Awesome, thank you. First of all, can everybody hear me okay? Not too loud? All right, cool. So hi, my name is Ivana. I am here representing Xanadu and our highlight product, PennyLane. So just right at the start, because there's a lot of us here, can we just give a quick hands up who has heard of PennyLane before? Oh, I'm very happy. I should have taken a photo of that. Who has used PennyLane? We're doing something well. Okay, I'm going to ask you at the end of this talk, there's going to be a little link to a survey, and it would be really fantastic if you wanted to tell us a little bit about your experiences with PennyLane, what kind of features you would love to have, what sucks, anything that comes to mind within the projects we're working on. We're really trying to work on this for the community and make sure everybody does amazing research and great projects. So, before we start, just a quick intro of myself. Like I said, hi, I'm Ivana. I am actually in Munich, which might sound a bit weird. Xanadu is in Toronto. There's very few of us who are scattered across the world, and I was very lucky to be able to attend here today. I'm a quantum physicist, so if you have some very technical questions about LLMV, LVM, or like QIR or MLIR, I might not be able to answer, but I will definitely find people in the company who will be able to figure that out after this talk. I have been in Xanadu for over a year now, and I guess we can go into the talk. If there's any questions, I know that normally today we've been dealing with questions at the end of the session, but this is a very long day, and I don't know how everybody's awake. It's been very exciting, but I'm feeling like if I keep talking for 45 minutes, that might not be the case. So if you have questions or you have a comment, please interrupt. Raise your hand. I hope that's okay with the organizers. No complaints? Okay, cool. Starting off then. So first of all, like I said, I'm going to just touch a little bit on the hardware, but focus mostly on PennyLane and our other software products and the cool stuff that you can do with it without bogging us all down at 5 p.m. on a Monday with more technical details. Well, some technical details. So first of all, Xanadu is a company that builds quantum computers with light. You might have heard about them, but in case you haven't, this is our motto. We want to build quantum computers that are useful and available to people everywhere, which I think is a sign that this company is still run by the people who founded it. We all know the state of the quantum industry at the moment, and I think this is a really cool advantage. It was founded 7 years and 2 weeks ago. We just celebrated our birthday. It's in Toronto. And we have almost 200 people at the company now. Xanadu is one of the, please don't sue me, I didn't come up with the term, unicorns. And if anybody calls us Xanadians, I might walk out. But this is our reality at the moment. We are trying to focus on hardware. This is why there's only one office for Toronto. We are working very hard to create photonic quantum computers that can run millions of qubits. Don't laugh, this is serious. This is our plan, this is our mission. Some of the papers that we've been working on, recently, if you're interested, this is the stuff that we have been touching upon. So SU2, sorry, I don't know, yeah, I can point, perfect. So SU2, variational circuits, noisy optical circuits, backpropagation, scaling, and parameterized circuits. We're doing a lot of research. We have published up until now a bit less than 100 papers. So we are really trying to be a company that does it all, and does it all successfully, and at the same time gives back to the community. So like I said, full stack. We have integrated chip design that we're working on. We have currently even available some quantum computers that you can access if you ask nicely. Some software products that I'm going to touch upon, and like I said, almost 100 research publications. I don't think I need to tell you about this background. I think everybody here knows what quantum computers are and what kind of technologies we have. But the one that we like the most at Xanadu at the moment is the one that we had out last year. So this was in June 2022. Xanadu demonstrated quantum advantage with Borealis. It had 216 squeeze-state qubits. We were very happy with it, and it was online for everybody to access for a year. We put it offline in June this year so that our hardware teams could focus on bringing you better and bigger quantum computers, which I think is very exciting. Yeah, so it doesn't look like this anymore, but it did look really cool, I promise. Now we just have a little clock. On to bigger and better things. I think, again, this is probably not the audience where I need to preach about the benefits of photonic quantum computers, but we all know that they're very easy to deal with. So Xanadu works with measurement-based quantum computing using continuous variables, and there's a lot of benefits here. We are hoping to make quantum computers that can be used at room temperature, that can be stacked, the chips of which can be stacked and which we can really blow up very quickly once we get things going. And of course, taking into consideration something that is apparently important in this audience, error correction flexibility. Very good. Whoopsie, how do I move on? There we go. All right, so like I said, there's some quantum computers that you can still access the X series that we have online. Borealis we put offline to focus on other stuff. And in our future, we are going toward here. So our hardware teams have been working on actually making this manufacturing process really nice and streamlined, and we hope to start working toward data centers in the upcoming years, or year, let's see. If you want any details on the actual hardware, because this is a software forum, I don't want to bog anybody down with the details, we have lovely visuals on our website, xanadu.ai. Please feel free to take a look. And as always, if you have any questions about our technologies, or our hardware, or our software, absolutely anything, one of the amazing things about Xanadu is that we are always, as company policy, we always answer questions. Whoever has anything to ask about what we're doing, how we're doing, we will find a way to answer their question and try to give them whatever it is they need, be it for research or curiosity, as far as we can, of course. We are partnering with some amazing organizations, and I think we're very proud of that. Some aren't included here more recently, such as Rolls-Royce, and we are having a nice little collaboration with Qbrate upcoming as well. Oh, we do have Rolls-Royce, I was wrong, sorry. And we are really, like I said, full stack. The important stuff, PennyLane. So I guess everybody here, most of you have heard about PennyLane, but please suffer with me, just in case there are people who are not super familiar, just to go through the basics to make sure everybody understands what's going on and why this is kind of a cool package. So, like I said, we really focus on our users. Any questions, super welcome, interrupt me even here. PennyLane is an open source Python library. Simple, easy, we've seen those. Except the difference is, this one is made natively for differentiable programming of quantum computers. Okay, so what does that mean? That means we took the buzzword bingo. I think this is what we needed on the bingo for the event, honestly. We took machine learning and we took quantum and we just took it together and said this is our brand now, and this is what PennyLane does best. It's not the only thing it does, but it's what it does best. We, of course, focus then on being able to train quantum computers like you would train a neural network, and naturally, because this is still the NISQ era, we are relying on hybrid algorithms for most of the things we do in practice. We are open source. You can find us on GitHub. Contribute, please. Send us your issues, feature request suggestions. We love to hear from you guys. We have a bunch of statistics here. And one of the things that I would really like to highlight, because it's been a lovely thing interacting with the community, is QHack, which Xanadu organizes. No, okay, I'm not talking about Xanadu again, because at QHack we have, it's a big quantum hackathon, happens every February. First part is coding challenges, they're in PennyLane. Second part is a hackathon, completely hardware, product agnostic, everything. But the coding challenges, I have to tell you, I think we have some winners in the audience here from this year. Do you want to say hi? Hi, congrats. So we have really cool prizes. If you're a student and you have some time in February, definitely consider participating. These guys won some NVIDIA GPUs, and they were really cool, I think. And I'm going to also say a bit more about this in the future, but I think this is really cool because our teams try to develop coding challenges every single year that are too difficult for our core software team to solve. And then teams from around the world come in and solve them in 10 hours. And this is really the type of community we're trying to build. Right, so basics. Quantum circuits. Differentiable? What the hell does that mean? Well, the fact is, if you squint, everything's differentiable, and we can treat everything as if it has some sort of parameters that we can throw into the quantum circuit, tune them, find the cost function, minimize it, ta-da, we've done some quantum machine learning. Of course, it's not that simple in practice, but the thing that we're trying to do really is to use quantum parameters within quantum circuits to train them and to find solutions to things, to use algorithms that we otherwise would not be able to. And doing it in PennyLane is much nicer than anywhere else because it is designed with this in mind, primarily. Yeah, like I said, I think we all know this. I can just skip the basics of what is machine learning. It's probably the wrong audience. So just as a top-down view, when we're looking at quantum circuits, we have some really basic things that we're looking at. We have initial states that are coming in. We have qubits that are on wires here for us. So this is actually a question that we get a lot. Xanadu focuses on photonic architectures, but we're developing PennyLane. Photonic architectures don't really mesh super well with qubit-based packages. This is something we're aware of. So if you're going to be using Xanadu's photonic quantum computers online, if you want to use a native package, you're going to be using something called strawberry fields. And if you haven't been following so far, our CEO is sort of obsessed with the Beatles. And we do have integrations between the two. So if anything comes up, you can always work in PennyLane and then do an integration towards strawberry fields. But yeah, so we're working with qubits. We have some gates here, parameters within these gates, and we measure. Easy peasy. We can look at this as if we're looking at what we call a Q node. So we have some inputs, we have some parameters that exist in the circuit, and we get some classical output. The way we would do this in PennyLane, we define a little device. We tell the device what the simulator is. It's going to have one wire in this really, really simple example. We define a circuit and use a decorator here to act on the device. We return expectation value. I mean, I have to be honest. When I first started learning PennyLane, this did not seem 100% intuitive, but then again, I'm a physicist, so figures. We also have, of course, this is useful for some of you who are working with very, I want to test this out kind of problems. We do have really nice visualizations now in PennyLane. That wasn't the case a year ago, so you can definitely use that to show your circuits and make it easier to follow things through. So, like I said, the stepwise process in dealing with variational algorithms is we have some sort of circuit, we make a Q node out of it, we specify a cost function, which is not always the easiest thing in the world. I think if you've been dealing with machine learning, you know that these kinds of things can be a little wibbly-wobbly, timey-wimey, a little bit confusing, a little bit difficult to prove, but this is why we work in this field, and we're trying to figure out what works best for us and for the problems we're working with. And we implement a training procedure. Ta-da! So once we've figured out how we're going to shove that into a circuit, it's relatively simple. We just separate our circuit into various different components, and we put them into PennyLane, and PennyLane does the work. So just before I actually go into fun stuff, I want to mention that PennyLane is mostly, or we try to be as much as we can, framework and hardware agnostic. What this means is, if you want to, and we're really building it to be future-proof, if you want to work on a particular type of quantum computing architecture, there's probably a plugin we've developed. There's a bunch. If you want to work Bracket, if you want to work with Qiskit, if you want to work with Rigetti, if you want to work with QR's atoms, IonQ, whatever comes to mind, we've got you covered. And also it integrates pretty seamlessly with stuff like TensorFlow and PyTorch and JAX, and of course NumPy. As a summary, PennyLane was built for automatic differentiation of circuits. It works really well with hybrid and classical models, no worries there. One thing that I haven't mentioned and we've been working on recently is we now support JIT compilation, just-in-time compilation. I don't know if there are any hands here who are not familiar with what this means in practice. Any brave hands? All right. So like very basic, just-in-time means if you're dealing with some sort of an algorithm and you are able to apply a JIT compiler to it, that means that as the compiler goes through the circuit, through the algorithm, it identifies the parts that are kind of getting executed most often and tries to optimize them which is a very nice approach to what we're doing, differentiable quantum computing. We have a bunch of templates and tools for optimization and machine learning, bunch of optimizers, bunch of whatever you need, and we're trying to be device independent. Applications. So I guess I feel like I'm preaching mostly to the choir. So if this is completely old news for you, I'm very sorry. You simply install PennyLane by pip install PennyLane. You can see an example of what the code looks like, but we're going to take a look at it a bit later on. And what you usually do is you have some sort of variational circuit, and you can combine it with a classical model to get something hybrid that works to solve your particular problem. And there's a lot of problems we can solve. And yeah, if we want to work on this interface between quantum and classical, we really need to be able to merge them together. So we have a bunch of simulators that are going to help you with this kind of stuff. And I don't think I want to touch upon them too much. I just want to highlight a couple of things, which is we do have these things we call lightning. These are not something we started off with, but we have the simulators that work with the C++ backend and that work really nice with NVIDIA's cuQuantum SDK. So if you haven't been following PennyLane development recently, this is what we've done. We're very proud of it, and I think it's a really nice thing that you're going to enjoy. We also have a bunch of other libraries in case you need them. We have Flaming Pi for photonic quantum error correction, Mr. Mustard, the Walrus, again, I'm very sorry. I'm not this much of a fan of the Beatles, and every time I look at this, I just have to wonder about what I'm doing with my life. And the thing that we've mostly been, or which part of our team has been mostly focusing on recently that's really new, is this just-in-time compilation with Catalyst. So I'm not going to go into detail because we have a couple of amazing blog posts in our documentation that can explain how this works, and then we have another one in preparation that tells you step by step how the backend is stitched together. But essentially, if you want to make sure that you have a JIT-compliant algorithm, literally all you do is do a little QJIT decorator above your Q node, and it also works when you use this function within JAX-compliant definitions. I don't know if anybody has noticed, we usually get feedback that people love the illustrations because they're very friendly. We have a graphic designer on our team now, and now they're cooler. I like them. Right, so the fields that we usually use PennyLane in, we talk about three of them. We have quantum computing, which covers a bunch of stuff that I think most researchers that are not fiddling around with machine learning are going to be interested in. For example, a lot of stuff with algorithms, complexity theory, figuring out architectures, hardware development, and so on. So it's kind of a good for all kind of a thing. We have, of course, quantum machine learning, where we're working to optimize variational circuits, and quantum chemistry, which we, I think, are going to be seeing the most interesting developments in the upcoming period. I think probably the chemistry folks here are going to agree with me, but I think some others might as well. So to help this kind of research and development, recently our team has introduced PennyLane datasets. What this means literally is that we are hosting datasets for very convenient and interesting molecules and Ising spin model and so on our website. You can visit them right here if you want to, and I even have a little video of how to do that. Literally have a bunch of molecules, you pick your favorite one, you figure out what you want to download, set your parameters, set the bases, and you're good to go. There we go. And this is all, of course, being constantly updated, but we just launched it like a month ago. So we're very proud of it, and we're hoping that it's going to help you folks work on whatever projects you're working on. You can see this in action inside of Visual Studio, I guess. Literally paste the code that the website spit out. You get your data set and action. So I think we think that part of the future of development of quantum-related libraries, packages, SDKs, whatever, is going to be in convenience. And convenience of use for research, for not having to figure out how do I use this, why does it take such a long time, just being able to go on and download something and move on with your life and focus on the research that matters. On to the research that matters. We have some recent developments also in the HPC and GPU use, and I'm just going to quickly mention it. So like I touched upon very lightly, that's almost a pun, we have 3 simulators that we like using with Lightning, which is optimizing the code that you're running in PennyLane. This is just a vanilla thing that you would run on a CPU. If you have GPU access, then it becomes a lot more interesting. Of course, we recommend NVIDIA SQ Quantum. And we also have Lightning Caucus, which works with all CPUs and GPUs supported by Caucus. If you want details, you can also find us online. I'm not going to pressure you to read any of this or try to teach you about details. I think the point here is it's Monday, 5 p.m. It's been a long day, and we have resources that make your life a lot easier. But all you need to know essentially is that if you have GPUs, we got you covered. If you want optimization for Mac, no worries. If you're trying to run something with a specific type of, I don't know, hardware, a specific number of qubits, we got you covered. And it's super simple to use. Literally, you change the simulator within the device definition and you move on with your life. So you can switch very quickly from a very local and non-interesting simulator to something a lot funner. As a quick example of what I'm talking about here, and I hope you forgive me that it's not in PennyLane colors, not everything can be apparently, we have here a small comparison of Lightning Qubit and Lightning GPU, where we also demonstrate that multi-threading works very nicely. So yay for HPC, and yay for the future development of coding that we're going to be able to do on these very cool systems, like the one at LRZ. I never know, is it LRZ or LRZ? How do we say it in English?
LRZ.
LRZ? Thank you. Let's go with LRZ, except I can't say the German R.
LRZ is also what Mark and Laura are using, I think. So
Okay, LRZ then. But actually, if you are from this area, we do have a really cool HPC workshop at LRZ in a couple of weeks. I do think it's completely booked out, though. Might be like a couple more places. Are we seeing anybody yet there? Nobody from here.
So the course is currently booked out, but you can join the waiting list, so we might.
But it's going to be online as well, right?
It's only going to be in person in the afternoon.
Okay. Well, hopefully we have more in the future.
So it will be in 2 weeks on the 23rd of 25th.
That's very helpful. Thank you. In any case, this is something that we've recently been working a lot on with NVIDIA and trying to develop with NVIDIA and other partners, of course, trying to develop very good systems that work efficiently on high-performance architectures, essentially, to give us cool results. Right. If anybody's actually interested in what we use, I think this is pretty straightforward. Everybody's doing the same thing. I don't think there's anything super interesting here for you guys. And like I mentioned, there's going to be a really nice blog post. It's going to explain a lot of the details on how we use Catalyst to implement JIT. So if you wait a couple of weeks and subscribe to our social channels, you'll be able to see that. Our developers have put a lot of effort into figuring that out. So, resources. I know that you guys have been using PennyLane, but I don't know if you've been using any of our tutorials and documentation and fun stuff. How many of you here are students, actually? Oh, that's a solid number. Nice. Have any of you used PennyLane in classes? Not yet. Okay, cool. I'm going to show you stuff that you can do to teach yourself PennyLane if you haven't used it before, or if you want to get better at it, and also some fun things. So, The truth is, I'm a physicist, but I don't work as a researcher at Xanadu. I'm part of what we call a community team, which I think is a relatively unique team in quantum companies at the moment, or quantum-focused teams at the moment. We do everything that has to do with multiple things at once, and users like you. So if there's an event, if there's a need to improve documentation, if you have suggestions for our devs to work on, you talk to us, we try to make it happen. We run a lot of open source software, we develop a lot of open source products, and we really want to make sure that the community is involved in them. Which means we develop resources to help you folks learn. We focus on making sure that everything we do is transparent, available, makes it simple for you to take on even the difficult stuff or the easy stuff if you start at a relative zero or something. We have a forum, we have a forum, Discuss PennyLane AI, where you can ask your questions about absolutely anything that has to do with Xanadu software that comes to mind, and we will answer it. You might give us a headache, but we will find an answer. We have a bunch of demos, tutorials, videos, blog posts that explain how the architectures that we work with work. We create coding challenges and hackathons. So I'm just going to quickly show you what this looks like. If I can do that with this angle, I wasn't expecting it. One sec. And that should do it. Yo, that's Catalyst. I'm not there yet. There's too many tabs, I'm sorry. I don't know how to manage my tabs. This is unfortunate. Okay, so I haven't opened it. This is fantastic. I should have been signed in. That apparently didn't happen either. So we've developed a platform, essentially, that we call PennyLane Challenges. If you've participated in any of our hackathons, coding challenges in the past, you might recognize what this looks like. But now you can log in and follow your progress, and you don't have to be part of an event to participate. Right now, we only have 6 challenges here. We'll be updating them as time goes on. But if you click on, I don't know, my first quantum simulation, you can see, well, you will have your history here. I haven't submitted anything. You can access all the resources you need here, and you get instructions for what kind of a coding challenge this is, what you're supposed to do, access to or suggestions or hints to what kind of documentation you should be looking into to solve it, and then right in the browser you can put your code in the white spaces, submit, get some useful feedback, learn, and get better at coding. Now, I know that this isn't for everyone. I'm certainly not a type of person that enjoys challenges, but it's a really, well, I don't enjoy coding challenges. I prefer learning in different ways, and I think there's a lot of different ways you can learn with. We have what we call the Quantum Code Book. Have you heard of this? Any nods? No, haven't heard, okay. So one of the things that we've noticed at Xanadu is that there's a lot of people who come into quantum computing who have a physics background and a relatively lacking software experience or skill set. Or we have software developers who are like, quantum computing sounds cool, what is quantum? And we've tried kind of meeting these two groups in the middle. Of course, there's no ideal way of doing this, but I think I opened this one. Fingers crossed, there we go. So we've tried making essentially a system, a learning tree. Okay, we don't want the tutorial. A learning tree for different types of quantum topics. So can anybody shout out a letter here for me?
A.
A, okay. Number? 3. And you're here and you can learn pair programming, learning outcomes. So you have 2 sides here. You have code and you have theory. Learning outcomes for theory, describing how the oracle can be applied to a pair of candidate solutions to determine if there's a secret combination, and determine the average number of queries required to find a solution when testing in pairs. You get actual full theory that is extremely useful for a physicist who understands linear algebra, who is comfortable with bras and kets, who knows what a unitary operator is, and who might, of course there's hints and solutions, and who might benefit from then taking a little peek on the left, once he's comfortable or she's comfortable with the side on the right. And software developers start with things that are a lot simpler when it comes to mathematics and physics involved, but which challenge them with, well, essentially coding challenges. And it functions in a similar way. So you cannot progress here until you've submitted the correct solution. So I can't even see the second one here to show you. But once you understand how something works in practice, it's much easier to understand the theory. And this is something we found to be very interesting when it comes to people trying to learn about the field. In fact, there's a colleague of mine who comes from a computer engineering background who, a couple of months ago, finished the entire code book, which is fairly impressive because we have more than 50 different chapters, and he feels very confident with quantum computing now. So if you ever like, I have a lot of time free, I'm about to board a plane or something, this is probably a good thing to take a look at because it's very user-friendly, and it takes you down baby steps to learn a particular topic in quantum computing. We have error correction, we have all kinds of stuff. I'm sorry, I can't continue the sentence. What do you want?
So always the first column is for the computer engineer and second column the proficiency, right?
Yeah, so the first column is, well, I wouldn't say that. So like actually, the way I would describe this is, okay, this is the one I wrote last. So you can see my drawings, pretty, right? So if you're a physicist, you're going to have an easier time looking through something like this. You're going to understand what's going on. You're going to be able to solve, okay, this is fairly simple. It's just the error correction bit flip code, or 3-qubit flip code, correction code. You're going to have an easier time understanding this, which means that when you look at the code, you might feel a little bit intimidated by, oh, what's a decorator? How do we deal with? What's a Q node? What is this device? Because sometimes when you're a physicist, you don't have a lot of exposure to pure code. But once you understand what's going on, it's easy to replicate it here. And for a software developer, we imagine, and know in most cases, that it's easier to go through this first, understand the practice, and then figure out what the theory actually wanted you to do, and understand obscure Greek letters. Hope that helps. Right. There's a couple of things I still wanted to just mention, which are our demos. And I think this is probably what most of you have interacted with, right? Oh, maybe not. Okay, so like I said, we really want to make sure that research is transparent, accessible, that it's open, essentially. So if you have a paper that you've been working on, that you've used PennyLane on, and you have your code and you're like, what do I do with this code? Nobody's going to see it. You can send it to us. We have a section of community demos where we just host your solutions so that you can prove that your results are actually replicable. And in addition to that, we also make our own demonstrations. So I don't think I'm going to have time, probably a good thing, to go through everything in detail. But for example, this is one of our most recent demos. Ooh, X, come on. There we go. This is one of our most recent demos that just implemented in PennyLane with some fun bells and whistles, QSVT. So this is a relatively recent algorithm, as you can read here. And the cool thing about our demos is, of course, you can read, you can see what's going on, but then you look on the right, and you can just go right ahead and download the notebook, the Jupyter notebook. So I already have it open here. So this means I can just go in here, and I can run the code, and whatever I want to change, I can change. I can adapt things. I have a really solid starting point, and I never have to go from zero. And okay, this is a really bad example of a diagram. We can do better. And if you get stuck, we also have related demos usually where, for example, this is an intro to QSVT. If you were looking at me like, what is QSVT? I've never heard of this before. You don't have to read the paper. We usually work very hard to try to explain it with theory, with code, with absolutely anything, and you can always download it and go right into it and code for yourself, because that's usually the best way of learning and being able to implement things very quickly. We never want you guys to start from zero. That's not cool. We're in a scientific environment, and we should be able to work off of each other's projects and each other's efforts. You can see some examples of the demos that we have. We have literally hundreds. I think if you're interested in anything from, if you're wondering how do photonic computers work, photonic quantum computers work, we have a really in-depth demo about this. I would super recommend it. It's super long, it's super detailed, has all the answers you need. If you're wondering about I don't know, neutral atoms, ZX calculus. Is quantum computing useful before fault tolerant? You can find a demo on it. And even the basics, like Grover's algorithm, or what is phase kickback, or how do I optimize qubit rotation? We got you covered. So yeah, that's a good place to start when you're trying to implement something. And we of course have, very recently we started a YouTube channel for PennyLane. There are some tutorial videos, but then there's also, my colleague Isaac, he records videos and he's been giving himself a little freedom, so there's also entertaining videos, like he forced 5 of our developers to code an optimization circuit blindfolded, and it went worse or better than you imagine. I could really recommend it. And of course, as I mentioned, QHack. So I'm not here to kind of do sales. This is not my job. I'm here to try to give you guys resources to make sure that everybody who is working in the quantum community has the opportunity to do cool stuff, that you know where to find the cool stuff, to make the cool stuff easier to find too, and then to try to get the entire community together to work on building our field as much as we can. So QHack is, I think, the largest quantum hackathon still. We get several thousand people attending, participating every year. It's going to be our 5th time. It's going to happen next February. And if you feel like testing out your coding skills or making a hackathon project with a team of up to 4 people, we can really recommend it. We're going to have cool prizes again. And if you go to the website, you can sign up for the newsletter and you get a little notification when it's up, when the registration is up. Just for context, in case you care, I don't know, statistics. I'm not doing sales, it doesn't matter to me, right? Next steps, join us. If you're already working in PennyLane, and even if you're not, and you think something like this might be cool, I think it's a very nice thing of all of us. I mean, we came here to an event that's called the Software Forum. We should be discussing, we should be interacting with each other. Personally, I found it difficult on Monday morning, but in theory, we really should. And if you are using the software and you have something that you would like to contribute to it, be it constructive feedback or some code, we'd be really, really happy to have you join. And if you have been using PennyLane, this is the link that I announced. It's a really, really short, less than a minute survey. bit.ly, bit.ly, I guess the back rows can't see. So bit.ly/PennyLane-survey, P, L, and S are capitalized. Oh, that's a PSA. PennyLane lane is capitalized. Sorry. Yeah, and that's, I think, what I had to say about our resources. If there's students here, and I now know that there are, we have the Xanadu residency program coming up. I know there's been other mentions of, and we're hiring. We're hiring, but this is also an internship sort of thing. So if you're a PhD student and you're thinking, I want some experience in industry, Xanadu is a really good place to do that. You can get really experience in hardware, software, pure research, even making codebook content. And I only included here the software and algorithms part of our careers board, but we're definitely still hiring. Xanadu is doing quite well, even despite the recent happenings in the tech industry. So we would really love to hear from you. And if you have any questions about any of this, let me know. I would be very excited to tell you more about it. So this concludes my little overview of how to work with PennyLane and what resources there are. I would just like to point out that if you have any questions about anything to do with our software, anything to do with our hardware, you can visit our forum. It's just discuss.pennylane.ai. We will answer your question. You might be upset, but we will answer it if it's complicated. We have newsletter, socials, Slack for questions, also if you prefer that, for Xanadu AI. You just visit the website, scroll down to the footer, same as on every other website. We also now, as of recently, have a PennyLane Discord server, which used to be the QHack Discord server, now it's PennyLane, so if you have questions or you want to hang out, that's also a good place. Definitely visit us on GitHub, and if you have a question or want to complain about something, you can also find my email address. It's just Ivana@xanadu.ai. And this is the benefit of working at a startup that I'm very happy about. And I think, yeah, that's about it. Thank you for your attention.
Thank you.